Hello dear students, welcome to the lecture 10 of software engineering course. Today's topic is,
Socio-Technical Systems.
okay, let's start. Today we will cover complex systems, systems engineering, systems procurement, system development and system operation. Systems.
Software engineering is not an isolated activity but is part of a broader systems engineering process. Software systems are therefore not isolated systems but are essential components of broader systems that have a human, social, or organizational purpose.
Okay, so for example,
Wilderness weather system is part of broader weather recording and forecasting systems. These include hardware and software, forecasting processes, system users, the organizations that depend on weather forecasts, etc.
so the socio-technical systems stack,
The socio-technical systems stack.
and there is society, organization, business process, application system, communications and data management, operating system and equipment. And other than society, they are all part of system engineering, and business process, application system, communication and data management and operating system are software engineering. So you see, this is a whole part of a system stack. These four elements are part of software engineering, and in addition, organization and equipment are completely systems engineering, and it is how it is. Okay.
Layers in the STS stack.
So the STS is Socio-Technical Systems stack. Equipment.
Hardware devices, some of which may be computers. Most devices will include an embedded system of some kind.
Operating system.
Provides a set of common facilities for higher levels in the system.
Communications and data management.
Middleware that provides access to remote systems and databases.
Application systems.
Specific functionality to meet some organization requirements.
Okay, layers in the STS stack is as follow: business processes.
A set of processes involving people and computer systems that support the activities of the business.
Organizations.
Higher-level strategic business activities that affect the operation of the system.
And society.
Laws, regulation and culture that affect the operation of the system. Society.
You see, society is also really important part of system development. You have to consider laws, of course, laws and regulation, and also the culture that affect the operation of the system. And holistic system design. One moment. Okay.
There are interactions and dependencies between the layers in a system and changes at one level ripple through the other levels.
For example,
change in regulations, society, leads to changes in business processes and application software.
For dependability, a system's perspective is essential.
Contain software failures within the enclosing layers of the STS stack. Understand how faults and failures in adjacent layers may affect the software in a system.
Okay. So complex systems.
A system is a purposeful collection of interrelated components working together to achieve some common objective. A system may include software, mechanical, electrical and electronic hardware and be operated by people. System components are dependent on other system components. The properties and behavior of system components are inextricably intermingled. This leads to complexity.
Okay, intermingled means strongly mixed. Okay. System categories are technical computer-based systems,
Systems that include hardware and software but where the operators and operational processes are not normally considered to be part of the system. The system is not self-aware. Example, a word processor used to write a book.
and socio-technical systems,
Systems that include technical systems but also operational processes and people who use and interact with the technical system. Socio-technical systems are governed by organizational policies and rules. Example, a publishing system to produce a book.
okay, and organizational affects process changes,
Systems may require changes to business processes, so training may be required. Significant changes may be resisted by users.
job changes,
Systems may de-skill users or cause changes to the way they work. The status of individuals in an organization may be affected by the introduction of a new system.
and organizational changes,
Systems may change the political power structure in an organization. If an organization depends on a system, then those that control the system have more power.
okay. Socio-technical system characteristics, emergent properties,
Properties of the system of a whole that depend on the system components and their relationships.
non-deterministic,
They do not always produce the same output when presented with the same input because the system's behavior is partially dependent on human operators.
So you see the difference of socio-technical systems mainly is this one. The system behavior is partially dependent on human operators. Okay, therefore it is not deterministic. Okay.
Complex relationships with organizational objectives. The extent to which the system supports organizational objectives does not just depend on the system itself.
Okay, so emergent properties are like this.
Properties of the system as a whole rather than properties that can be derived from the properties of components of a system.
And
Emergent properties are a consequence of the relationships between system components.
okay, and
They can therefore only be assessed and measured once the components have been integrated into a system.
okay, examples of emergent properties. There is property description. So the property volume,
The volume of a system, the total space occupied, varies depending on how the component assemblies are arranged and connected.
reliability,
System reliability depends on component reliability, but unexpected interactions can cause new types of failures and therefore affect the reliability of the system.
security,
The security of the system, its ability to resist attack, is a complex property that cannot be easily measured. Attacks may be devised that were not anticipated by the system designers and so may defeat built-in safeguards.
repairability,
Repairability?
okay,
This property reflects how easy it is to fix a problem with the system once it has been discovered. It depends on being able to diagnose the problem, access the components that are faulty, and modify or replace these components.
okay, and usability,
This property reflects how easy it is to use the system. It depends on the technical system components, its operators, and its operating environment.
Usability is also very important for clients, of course, because if system may be extremely complex, advanced, good, well, however, if its usability is poor, you may have hard time to sell it simply. Therefore, usability is really important. Never take it lightly. Types of emergent property: functional properties.
These appear when all the parts of a system work together to achieve some objective. For example, a bicycle has the functional property of being a transportation device once it has been assembled from its components.
And non-functional emergent properties.
Examples are reliability, performance, safety, and security. These relate to the behavior of the system in its operational environment. They are often critical for computer-based systems, as failure to achieve some minimal defined level in these properties may make the system unusable.
Okay, and reliability as an emergent property.
Because of component interdependencies, faults can be propagated through the system. System failures often occur because of unforeseen interrelationships between components. It is practically impossible to anticipate all possible component relationships. Software reliability measures may give a false picture of the overall system reliability.
Influences on reliability. Hardware reliability is.
What is the probability of a hardware component failing, and how long does it take to repair that component?
Okay, and software reliability.
How likely is it that a software component will produce an incorrect output? Software failure is usually distinct from hardware failure in that software does not wear out.
And operator reliability.
How likely is it that the operator of a system will make an error?
Actually, this is the most common incident that causes problem in nowadays, because usually the big systems are programmed and checked and verified by many different teams, experts. Therefore, systems usually do not have any weaknesses, invulnerabilities, exploits, and such. However, operators may always make an error, a mistake. They can be deceived, and even though you have a bulletproof system, if your operator makes a mistake, your system will make mistake, produce error, and such. Okay, will fail.
Failures are not independent and they propagate from one level to another.
Okay, and failure propagation is layered like this. Okay, so you see initial failure comes from hardware and it is propagated to software level, then it is propagated to operating level, then operating level propagates to software level, then failure consequence is gets to hardware level. Okay.
Non-determinism. A deterministic system is one where a given sequence of inputs will always produce the same sequence of outputs. Software systems are deterministic. Systems that include humans are non-deterministic. A socio-technical system will not always produce the same sequence of outputs from the same input sequence. Human elements. People do not always behave in the same way.
And system changes, another thing.
System behavior is unpredictable because of frequent changes to hardware, software, and data.
Okay, so the success criteria.
Success criteria.
Okay, success criteria.
Complex systems are developed to address wicked problems, problems where there cannot be a complete specification. Different stakeholders see the problem in different ways and each has a partial understanding of the issues affecting the system.
Okay.
Consequently, different stakeholders have their own views about whether or not a system is successful. Success is a judgment and cannot be objectively measured. Success is judged using the effectiveness of the system when deployed rather than judged against the original reasons for procurement.
Okay, conflicting views of success.
MHCPMS designed to support multiple, conflicting goals.
Okay, and
Improve quality of care. Provide better information and care costs and so increase revenue.
okay. And fundamental conflict is such as
To satisfy reporting goal, doctors and nurses had to provide additional information over and above that required for clinical purposes. They had less time to interact with patients, so quality of care reduced. System was not a success. However, managers had better reports. System was a success from a managerial perspective.
so you see within a system different components can have different successes, success criteria, success rates and such.
Systems engineering. Procuring, specifying, designing, implementing, validating, deploying and maintaining socio-technical systems. Concerned with the services provided by the system, constraints on its construction and operation and the ways in which it is used to fulfill its purpose or purposes. Stages of systems engineering.
Stages of system engineering, procurement stage, and then equipment and software updates, and then it moves to development stage. Then development stage moves to system evolution and operation. So this is the stages of system engineering. Okay.
Why STEM's engineering stages.
Sorry.
Systems engineering stages.
Okay.
Procurement acquisition.
So the procurement stage is acquisition stage actually.
The purpose of the system is established, high-level system requirements are defined, decisions are made on how functionality is distributed and the system components are purchased.
Okay, and
Development. The system is developed, requirements are defined in detail, the system is implemented and tested and operational processes are defined.
operation.
The system is deployed and put into use. Changes are made as new requirements emerge. Eventually, the system is decommissioned.
Okay.
Security and dependability considerations. Design options limited by procurement decisions. Purchased components may make some safeguards impossible to implement. Human errors made during development may introduce faults into the system. Inadequate testing may mean faults are not discovered before deployment. Configuration errors during deployment may introduce vulnerabilities. Assumptions made during procurement may be forgotten when system changes are made.
Okay.
Professional disciplines involved in systems engineering.
So you see systems engineering is a higher level of software engineering, and these disciplines are involved architecture, electrical engineering, mechanical engineering, civil engineering, electronic engineering, ergonomics, user interface design, software engineering, and when all of them gets together, systems engineering appears, or let's say gets composed.
Interdisciplinary working. Communication difficulties. Different disciplines use the same terminology to mean different things. This can lead to misunderstandings about what will be implemented. Differing assumptions. Each discipline makes assumptions about what can and can't be done by other disciplines.
Okay. And professional boundaries.
Each discipline tries to protect their professional boundaries and expertise, and this affects their judgments on the system.
Okay, so what are the key points of the first part?
Socio-technical systems include computer hardware, software, and people, and are designed to meet some business goal. Human and organizational factors, such as the organizational structure, have a significant effect on the operation of socio-technical systems. Emergent properties are properties that are characteristic of the system as a whole and not its component parts. The fundamental stages of systems engineering are procurement, development, and operation.
Okay. So, part 2, I will take a pause. Okay, so Socio-Technical Systems Part 2, System Procurement.
Acquiring a system or systems to meet some identified organizational need. Before procurement, decisions are made on
Scope of the system. So what will be the scope of the system? System budgets and timescales. Of course, before you start system development, you have to plan its budget and timescales, high-level system requirements.
Based on this information, decisions are made on whether to procure a system, the type of system, and the potential system suppliers.
Okay, decision drivers. So, what causes us to make that particular decision? Okay,
The state of other organizational systems. The need to comply with external regulations. External competition. Business reorganization.
and available budget. Okay, procurement and development.
Some system specification and architectural design is usually necessary before procurement. You need a specification to let a contract for system development. The specification may allow you to buy a commercial off-the-shelf COTS system. Almost always cheaper than developing a system from scratch. Large complex systems usually consist of a mix of off-the-shelf and specially designed components. The procurement processes for these different types of component are usually different.
For example, let's say you are going to develop a game and you wouldn't try to develop from scratch a let's say engine to draw graphics, because it would be too expensive, time consuming and such. Therefore you would buy a license for graphic engine and use it, and you also develop some other parts at your development team, or let's say you may buy assets as well. So it is mix of off the shelf and specially designed components, usually in large and complex systems.
System procurement processes.
Okay, so first you start with define business requirements, then survey market for existing systems. the shelf system available, if it is available, adapt requirements, and assess existing systems, choose system supplier, and negotiate contract. If off-the-shelf system is not available, then you go to custom system required, define requirements, issue request to do tender, select tender, and negotiate contract. Okay. However, if you don't buy from off-the-shelf system, it is usually generally much more expensive than buying off-the-shelf system. The developing from scratch is much more expensive because when you buy off-the-shelf system, that means that it is sold to many clients, therefore it is cheaper. Okay.
Procurement issues. Requirements may have to be modified to match the capabilities of off-the-shelf components. The requirements specification may be part of the contract for the development of the system. There is usually a contract negotiation period to agree changes after the contractor to build a system has been selected.
Okay.
Contractors and subcontractors. The procurement of large hardware, software systems is usually based around some principal contractor. Subcontracts are issued to other suppliers to supply parts of the system. Customer liaises with the principal contractor and does not deal directly with subcontractors.
Okay.
Procurement and dependability. Procurement decisions have profound effects on system dependability as these decisions limit the scope of dependability requirements. For an off-the-shelf system, the procurer has very limited influence on the security and dependability requirements of the system. For a custom system, considerable effort has to be expended in defining security and dependability requirements.
Okay. System development
Usually follows a plan-driven approach because of the need for parallel development of different parts of the system. Little scope for iteration between phases because hardware changes are very expensive. Software may have to compensate for hardware problems. Inevitably involves engineers from different disciplines who must work together. Much scope for misunderstanding here. As explained, different disciplines use a different vocabulary and much negotiation is required. Engineers may have personal agendas to fulfill.
Okay, systems development. Requirements development. First it is done, then system design is done, then subsystem engineering, then system integration, then system testing, and finally system deployment.
System requirements definition. 3 types of requirement defined at this stage. Abstract functional requirements. System functions are defined in an abstract way, system properties. Non-functional requirements for the system in general are defined, undesirable characteristics. Unacceptable system behavior is specified.
Okay, then
Should also define overall organizational objectives for the system. The system design process.
partition requirements, organize requirements into related groups, identify subsystems, identify a set of subsystems which collectively can meet system requirements, assign requirements to subsystems, causes particular problems when costs are integrated, cost of the shell systems, specify subsystem functionality, define subsystem interfaces, critical activity for parallel subsystem development. Okay, so the interfaces are also important when you do parallel subsystem development. And requirements and design.
Requirements engineering and system design are inextricably linked. constraints posed by the system's environment and other systems limit design choices, so the actual design to be used may be a requirement. Initial design may be necessary to structure the requirements. As you do design, you learn more about the requirements.
Okay. Requirements and design spiral is shown like this. Start, domain and problem understanding, requirements elicitation and analysis, architectural design, review and assessment. And this is a looping process, and system requirements and design documentation. Finally, it is done. The documentation is made.
Subsystem development. Typically parallel projects developing the hardware, software and communications may involve some COTS, commercial off-the-shelf systems procurement. Lack of communication across implementation teams can cause problems. There may be a bureaucratic and slow mechanism for proposing system changes, which means that the development schedule may be extended because of the need for rework.
Okay. And system integration.
The process of putting hardware, software and people together to make a system should ideally be tackled incrementally so that subsystems are integrated one at a time. The system is tested as it is integrated. Interface problems between subsystems are usually found at this stage. May be problems within coordinated deliveries of system components.
Okay, then system delivery and deployment.
After completion, the system has to be installed in the customer's environment. Environmental assumptions may be incorrect, may be human resistance to the introduction of a new system. System may have to coexist with alternative systems for some time, may be physical installation problems, e.g. cabling problems, data cleanup may be required, operator training has to be identified.
Okay. Development and dependability.
Development and dependability.
Okay.
Decisions are made on dependability and security requirements and trade-offs made between costs, schedule, performance and dependability. Human errors may lead to the introduction of faults into the system. Testing and validation processes may be limited because of limited budgets. Problems in deployment mean there may be a mismatch between the system and its operational environment.
And system operation.
Operational processes are the processes involved in using the system for its defined purpose. For new systems, these processes may have to be designed and tested and operators trained in the use of the system. Operational processes should be flexible to allow operators to cope with problems and periods of fluctuating workload.
Okay, and human error.
Human errors occur in operational processes that influence the overall dependability of the system. Viewing human errors, the person approach makes errors the responsibility of the individual and places the blame for error on the operator concerned. Actions to reduce error include threats of punishment, better training, more stringent procedures, etc. The system's approach assumes that people are fallible and will make mistakes. The system is designed to detect these mistakes before they lead to system failure. When a failure occurs, the aim is not to blame an individual but to understand why the system defenses did not trap the error.
Okay, I think this is really important. When you're developing a system, you have to always consider that the operator may make mistakes. Therefore, you have to take precautions and try to quarantine, take into quarantine that error. Okay, so with this approach you may prevent system failure, you may prevent damage to the system. Also, you should consider the fact that the operator may have malicious intentions. However, usually it is very hard to take precautions for that, but if it is possible, you should also consider the operator as a hacker. Okay, and it would even make your system stronger and make it lesser unsecure. For example, in the previous lectures I have shown you how very recent Twitter hack has happened. It was a social engineering attack, and if Twitter had precaution systems to detect such unusual behavior from its operators, they may have prevented such hack event from happening. Okay, so you need to consider everything of this, every one of these when developing a system. So system defenses.
To improve security and dependability, designers should think about the checks for human error that should be included in a system. As I discuss in later parts, there should be multiple, redundant barriers which should be different, diverse.
No single barrier can be perfect.
There will be latent conditions in the system that may lead to failure.
However, with multiple barriers, all have to fail for a system failure to occur, which is very true. Therefore, you should put multiple barriers to prevent system failure, especially in critical systems, health critical systems or such systems. Failure is not an option, is not acceptable. Therefore, it is really important.
Reasons Swiss cheese model of system failure.
Okay, so you see active failure, human error, for example, and there are barriers. You see there are 4 barriers, and every one of them has to fail for system to failure. Okay.
Defenses in an ATC system.
Conflict alert system raises an audible alarm when aircraft are conflicting paths. So ATC is aircraft. What can it be? Aircraft transfer system. Oh, it is air trade center. Maybe no. Yeah, air traffic control system. Okay. So in an air traffic control system, there are multiple defenses. What are they? Conflict alert system. If aircrafts are on conflicting paths, an audible alarm goes off. So the operator gets warned about that with a physical alarm. Recording of instructions allows instructions issues to be reviewed and checked. And so if there are instructions that are against the policies, against the rules defined to defend the system, they may be blocked from further execution, and maybe some other personnel can be alerted. It is totally up to you how you design the system. And sharing information, the team of controllers cross-check each other's work, this is a very good defense system. If there are multiple operators, the chances of all of them failing is much lower than a single one. It is like a write disk system. When we do a write disk, all of them, when we do a write one, for example, all of the disks has to fail for us to lose data. And system evolution.
Large systems have a long lifetime. They must evolve to meet changing requirements.
Evaluation is inherently costly.
Changes must be analyzed from a technical and business perspective. Subsystems interact so unanticipated problems can arise. There is rarely a rationale for original design decisions. System structure is corrupted as changes are made to it.
Okay. Existing systems which must be maintained are sometimes called legacy systems. Evaluation and dependability.
Changes to a system are often a source of problems and vulnerabilities. Changes may be made without knowledge of previous design decisions made for security and dependability reasons. Built-in safeguards may stop working. New faults may be introduced or latent faults exposed by changes. These may not be discovered because complete system retesting is too expensive.
This is so true. When you make a change, it is really hard to be sure that it is not breaking any of the working systems, any of the existing systems. Therefore, it is costly. It is somewhat dangerous. When you first time develop and deploy a system, you make all the tests. Okay, and after system have been working for a long time, if you make changes, it is really hard to be sure that it is not breaking any of the previously tested or working systems. Okay. So the key points of the second part is as follows.
System procurement covers all of the activities involved in deciding what system to buy and who should supply that system. System development includes requirements, specification, design, construction, integration, and testing. When a system is put into use, the operational processes and the system itself have to change to reflect changing business requirements. Human errors are inevitable, and systems should include barriers to detect these errors before they lead to system failure.
Okay. So, are there anything else that is important for this lecture? Let's read the key points of first part again.
Socio-technical systems include computer hardware, software, and people, and are designed to meet some business goal. Human and organizational factors, such as the organizational structure, have a significant effect on the operation of socio-technical systems. Emergent properties are properties that are characteristic of the system as a whole and not its component parts. The fundamental stages of systems engineering are procurement, development, and operation.
Okay, I think we can end this lecture. All right, so please determine your projects already and tell me about your project details from email or Discord and verify that it is fine to do it. If you have any questions, you can always email me, ask me through Discord. So, end of lecture.